Welcome to this video, and in this video we'll be looking at the time solutions of the state equations. Look at the time solution of state equations. We've been able to model any given control system in state space using the state equation and the output equation as x of t derivative is ax of t plus bu of t, and y of t is cx of t plus du of t. And of course, this is for linear time invariant systems. We would desire to obtain the solutions for our x of t and y of t given the state equation and the output equation as the state space model for our given control system. And therefore, in this discussion, we look at the time solution of this equation given that they are the state equation and the output equation of any given system. We start our discussion with the first case, or case 1, where we have a homogeneous case. And in a homogeneous case, then the input u of t is equal to 0. Our state equation can be written as x derivative of t is equals to ax of t, where a is a scalar. So we start our discussion on the solution of the state equation given that a is a scalar and the system is homogeneous, that is u of t is equals to 0. From this equation, we can write in Laplace form as x of s plus minus x of 0, minus x of 0 minus x of 0 will be equal to ax of s. If we collect the like terms together, we'll have s minus a into x of s will be equal to x of 0, from which we can obtain our x of s to be equal to 1 over s minus a x of 0. And if we transform into inverse Laplace transform, or we obtain the inverse Laplace transform, then our x of t will be equal to exponential at x of 0. And this is the solution of the state equation when a is a scalar. Let's extend the same to when a is a matrix. We can write our x of t derivative is ax of t. We can write this in Laplace form as x of s will be equal to sx of s minus x of 0, the initial condition, will be equal to ax of s. Again, if you've got to collect the like terms together now, because A is a matrix, we multiply S with an identity matrix of the same order as A to obtain Si minus A. X of S will be equal to X of 0, from which we get our X of S to be equal to, we divide both sides by Si minus A to get Si minus A inverse multiplied by x of 0. If we get the inverse Laplace transform on both sides, then we get x of t to be equal to the inverse Laplace transform of Si minus A inverse multiplied by x of 0. And this is the solution when A is a matrix. The solution when A was a scalar was x of t is exponential at x of 0. And if we compare the two, then we have this term which can be compared with exponential at and can be written as exponential at, capital A for a matrix, is given by the inverse Laplace transform of Si minus A inverse. And this expression of exponential at is the inverse Laplace transform of Si minus A inverse is called the state transition matrix. This is called the state transition matrix. Our solution therefore can be written as x of t is equals to exponential at x of 0. From this, we notice then that if we have our state transition matrix and the initial conditions of the system, then we can solve for x of t. And therefore, the state transition matrix is basically a matrix whose values, with the help of the initial conditions, helps us determine the states of our given system for a homogeneous system. Let's take an example or an illustration on the determination of the state transition matrix towards the solution of a homogeneous state equation. We'll take an example. We are to obtain the state transition matrix of the state equation, determine the state transition matrix of the state equation x1, x2 derivative is equals to 0, 1, minus 2, minus 3 into x1, x2. You notice that this is a homogeneous case since our u of t is 0. The state transition matrix is defined by exponential at is the inverse Laplace transform of Si minus A inverse. The inverse Laplace transform of Si minus A inverse is our state transition matrix. Our Si minus A is the matrix. We multiply S by an identity matrix 2 by 2 and we subtract A to get S minus 1, 2, S plus 3. Then Si minus A inverse will be 1 over the determinant, which is S squared plus 3S plus 2 into, we interchange the terms of the major diagonal, S plus 3S, negate the terms of the minor diagonal to negative 2 and 1, which we can write our Si minus A inverse is given by 1 over, we can write this in terms of its factors or its roots as S plus 1 into S plus 2, then into S plus 3, 1 minus 2S. This can be written as S plus 3 over S plus 1 into S plus 2, 1 over S plus 1 into S plus 2, negative 2 over S plus 1 into S plus 2, and S over S plus 1 into S plus 2. This is our Si minus A. Next, we need to determine the inverse Laplace transform for these. You notice then we've got to put these into partial fraction form for each of the parts of the matrix. So we determine the partial fraction form for each of the parts. Let's take the first one. S plus 3 over S plus 1 into S plus 2 can be written as A over S plus 1 plus B over S plus 2, where A is S plus 3 over S plus 1 when S plus 2 when S is negative 1, which will give us 2 over 1, which is 2. Our B will be equal to S plus 3 over S plus 1 when S is minus 2, which will give us 1 over negative 1, which is negative 1. So this can be written as 2 over S plus 1 minus 1 over S plus 2. Next, we have 1 over S plus 1 into S plus 2, which can be written as 1 over S plus 1 into S plus 2, can be written in partial parts as C over S plus 1 into or plus D over S plus 2, where C is 1 over S plus 2 when S is negative 1, which will give us, if we evaluate this, we get this to be 1. And our D will be 1 over S plus 1 when S is negative 2, and this will give us negative 1. Therefore, this can be written as 1 over S plus 1 minus 1 over S plus 2. Next, we have negative 2 over S plus 1 into S plus 2. So we have minus 2 over S plus 1 into S plus 2 can be written as E over S plus 1 plus F over S plus 2, where E will be equal to minus 2 over S plus 2 when S is negative 1, which will be minus 2 over 1, which is negative 2. Then our F will be minus 2 over S plus 1 when S is negative 2, which will be negative 2 over negative 1, which is 2. And therefore, we can write this as minus 2 over S plus 1 plus 2 over S plus 2. Lastly, we can have the last term was S over S plus 1 into S plus 2. This can be written as S over S plus 1 into S plus 2 will be equal to G over S plus 1 plus H over S plus 2, where G will be given by S over S plus 2 when S is negative 1, which will be equal to negative 1 over 1, which is negative 1. Our H will be given by S over S plus 1 when S is minus 2, which will be negative 2 over negative 1 to get 2. And therefore, this can be written as negative 1 over S plus 1 plus 2 over S plus 2. That means then we want to determine our exponential AT, which is the inverse Laplace transform of our terms. So we have 2, negative 1. So this is 2 over S plus 1 minus 1 over S plus 2. The other terms are 1, negative 1. We have 1 over S plus 1 minus 1 over S plus 2. the other terms, we have negative 2 and 2. So minus 2 over s plus 1 plus 2 over s plus 2. And finally, we have negative 1 over s plus 1 plus 2 over s plus 2, which will be equal to, so this one will give us 2 exponential minus t minus exponential negative 2t. Then this gives us exponential minus t minus exponential negative 2t. This one will give us minus 2 exponential minus t plus 2 exponential negative 2t. Lastly, we'll have minus exponential negative t plus 2 exponential minus 2t. And this is our state transition matrix. We extend the same discussion to a non-homogeneous case. Case 2 is when we have a non-homogeneous case. That means u of t is not equal to 0. Again, we can adopt the simple state equation as x of t derivative is ax of t plus bu of t, where a and b are scalars. So a and b are scalar quantities. Then we move on to the condition where a and b are matrices. From this, if we take this equation and call this equation 1, if we multiply equation 1 by exponential negative at, if we multiply 1 by exponential negative at, we'll get exponential negative at x of t will be equal to exponential negative at a x of t plus exponential negative at bu of t. We'll call this equation 2. If we collect the like terms together, takes the x of t to this side, then we'll have exponential minus at into x of t minus ax of t. We'll factor out exponential negative at, which will be common, and then we subtract ax of t will be equal to exponential negative at bu of t. We can call this equation 3. We notice that exponential negative at into x derivative of t minus ax of t can be written as the first derivative with respect to t of exponential at negative x of t. Can confirm that the whole of this expression is the first derivative of exponential negative at x of t. That means we can write equation 3 as follows. The first derivative with respect to t of exponential at x of t is equals to exponential negative at b u of t. If we integrate both sides, we'll have exponential negative at x of t is the integral from 0 to t, the integral from 0 to t of exponential negative at b u of t plus a constant, and that constant is our x of 0. If we want to get x of t, we divide both sides by exponential at to get x of t will be equal to, I'll start with this term. If I divide by exponential negative at, it will be exponential at x of 0 plus, then this term will be exponential at the integral from 0 to t of exponential negative at b ut dt. You notice if we evaluate the integral directly, then there will be a cancellation taking place here. And to avoid that, which is similar to what we call pole zero cancellation in control systems, then we change the second term, instead of a function of t, we change it into a function of a different variable called maybe tau, and then we avoid the pole zero cancellation, from which we can write x of t will be exponential at x of 0 plus exponential at, the integral from 0 to t of exponential negative a tau b u tau d tau, which we can now write as, we can now factor these together because they are on a common base, and write these as our x of t will be exponential at x of 0 plus the integral. If you combine these two, you'll get exponential a into t minus tau. So this becomes exponential a into t minus tau, then b u of tau d tau. And this becomes the time solution of the non-homogeneous state equation. We can notice that the solution has two parts. One part which is dependent on the initial conditions of the system x of 0, so this part, and another part that depends on the input to the system u of tau. And the solution of a homogeneous state equation will have two parts. One part which is dependent upon the initial conditions of the system, and another part dependent upon the inputs of the system. And in our case, the term dependent on the initial condition is multiplied with our exponential at, and this one is multiplied by exponential a into t minus tau. If we extend this or compare this with the state equation where a and b are matrices, that is x derivative of t is equals to a x of t plus b u of t, then the solution will take the form of x of t will be equal to, so instead of now exponential small at, we have this as exponential at x of 0 plus the integral from 0, so the integral is from 0 to t, of exponential a, capital A, into t minus tau, b, capital B, for a matrix, and u of tau d tau. And this is the solution of a homogeneous state equation with A and B being matrices. It's good to point out that when you have the state transition matrix exponential AT, to transform into exponential A into t minus tau, basically means where there is t in the state transition matrix, we replace with t minus tau. And therefore, the transformation will involve the replacement of t with t minus tau in the state transition matrix when obtaining the solution for the non-homogeneous state equation, given that A and B are matrices. Finally, I'll take an example. And in the example, we are to obtain the time response of the state equation. We obtain the time response of the state equation, x1, x2 derivative is equals to 0, 1, minus 2, minus 3, x1, x2, plus 0, 1, u, given that the input is a unit step input. That means u of t is a unit step input. That means is equals to 1. The solution of the state equation is x of t is given by exponential at x of 0 plus the integral from 0 to t of exponential a into t minus tau b u of tau v tau. First, we need to determine the state transition matrix. We determine the state transition matrix exponential at, which is the inverse Laplace transform of si minus a inverse. And it's good to note that the same matrix A is what we had previously in our example on the homogeneous case. This matrix is the same, and therefore its state transition matrix will not change. So I will be adopting the same state transition matrix given by this equation or expression as exponential at is given by this matrix. If we can proceed and adopt that, then we can have our exponential at is given by, so it was given by 2 exponential negative t minus exponential negative 2t, then exponential minus t minus exponential negative 2t, then this was minus 2 exponential minus t plus 2 exponential minus 2t. Lastly, we had this as negative exponential negative t plus 2 exponential minus 2t. Next, we need to determine exponential a into t minus tau, and we said into the state transition matrix, where there is t, we replace that with t minus tau. And therefore, into this expression, where there is t, we replace with t minus tau to get our exponential a into t minus tau will be the matrix. The first term will be 2 exponential minus t minus tau minus exponential negative 2 into t minus tau. The second term will be exponential minus t minus tau minus exponential minus 2 into t minus tau. Then this term is minus 2 exponential minus t minus tau, and then plus 2 exponential minus 2 into t minus tau. Lastly, we'll have minus exponential negative t minus tau plus 2 exponential minus 2 into t minus tau. That is our exponential at minus tau. Next, we need to determine exponential at tau multiplied by b and u. Our u is 1, so the implication of multiplication by u will not change that. So we multiply that by b, which is 0, 1. And therefore, our exponential a into t minus tau multiplied by b will mean we multiply this matrix by 0, 1. So if we multiply this, this will be 0, and this will be this term times 1, then this 0 and this term times 1. Therefore, we end up with the terms of this matrix here, which will be exponential minus t minus tau minus exponential negative 2 into t minus tau, then minus exponential minus t minus tau plus 2 exponential minus 2 into t minus tau. Next, we need to determine the integration from 0 to t of the product we obtained with respect to tau. So we integrate, therefore the integral from 0 to t of exponential a t minus tau b d tau will be the integral from 0 to t of exponential minus t minus tau minus exponential minus 2 into t minus tau, then negative exponential minus t minus tau plus 2 exponential minus 2 into t minus tau d tau. So our matrix is at this point, which we are integrating. So we integrate that, then we will get this as follows. So integrate this term with respect to tau. Notice exponential negative t will be held as a constant. Exponential tau integrated will still give us exponential tau, and therefore this term remains. Then this term will give us exponential negative 2t as a constant, and then exponential to positive 2 tau integrated will give us a half exponential 2 tau. This and these terms are the same. And then because of these two, the only difference between these two and this is their half will cancel out with 2, and we will end up with our terms as follows. So we'll have the integral being equal to exponential negative t minus tau minus or plus, let's confirm that term. This is minus, this is negative, so it will be minus a half minus a half exponential minus 2 into t minus tau. Then the other one will be negative exponential negative t minus tau plus exponential minus 2 into t minus tau. And the limits are from 0 to t. So for the first one, when tau is t, the whole of this will be 1 minus. When tau is t, the whole of this will be 1, so minus a half minus. Then when tau is 0, we'll have exponential minus t minus a half exponential minus 2t. Then these terms will be negative 1 when tau is t, and then plus when tau is t, again this will be 1, minus when tau is 0, we'll have a negative exponential negative t plus, then this will be exponential negative 2t. And this will give us, this will be equal to, this will give us a half minus exponential negative t plus a half exponential negative 2t. Then this will be 0, then we'll get exponential minus t minus exponential negative 2t. And this is our term, the integral from 0 to t of exponential a into t minus tau b u of tau d tau. This is the second part. Finally, to obtain the solution for our x of t, which we said is exponential at x of 0 plus the integral from 0 to t of exponential a into t minus tau b u of tau d tau will be, we take the state transition matrix and we multiply by x of 0, which was 2 exponential minus t minus exponential negative 2t. The second term was exponential minus t minus exponential negative 2t. Then minus 2 exponential minus t plus 2 exponential negative 2t. The other term was minus exponential negative t plus 2 exponential negative 2t. This one we multiply by x1 of 0 and x2 of 0 plus this integral, which we have evaluated to this part, and this will be equal to plus a half minus exponential negative t plus a half exponential negative 2t. And this is exponential negative t minus exponential negative 2t. And this becomes the time solution of our given state equation. Notice if the initial conditions of x1 and x2 are given, then we would proceed to simplify this further to obtain the perfect solution for our x of t. And that is the solution of the homogeneous, non-homogeneous state equation with two parts. One part depends on the initial conditions, and the second part which depends on the input to the system. And thank you for watching the video.